Okay, so today we're gonna continue talking about differential equations, especially the ordinary differential equations. Last time we talked about the fact, a pretty cool fact, that all the high-order differential equations can, in principle, be turned into first-order equation arrays. We took the look of a fourth-order equation. It's a very it's a fixed procedure. So you just go from y to y prime all the way to highest order of derivative, you can turn that into a first order equation arrays. So last time at the end of the class, we didn't have the right-hand side. Now the warm-up problem is we look at the third order differential equation, but we have a right-hand side. The question is how to turn this into a set of first order equation arrays. Let's think for about 20 seconds or so. Okay, so let's work with the procedure. We define a new vector called yt. This yt always look like first one is the scalar yt. Then I take the derivative. I stop at one order less than the highest order here. So it's in R3. Now I just take derivative, dt. So the first component is y prime t. Second component is y double prime t. Third component is y triple prime t, but this is nothing but the equation. This is really the most important part, because of these two, they always look like that. It doesn't involve the equation at all. Now I would like to write it in terms of a matrix times y. This is possible. And because here I have a y prime, so this is 0, 1, 0. Here I have a yt, y prime, y double prime. This one, you obtain that should be 0, 0, 1. And let's see. Okay, and finally, this one, we need to use the equation. So this is minus y double prime t. So this is 0, 0, minus 1. And here we have a right-hand side ft. So we separate that because that's the inhomogeneous part. And here we put a ft here. So this one, we have converted the scalar higher order differential equation into a vector first order differential equation. Here, this matrix is A, yt plus f vector t, and this is our f vector t. It always looks like 0, 0 something. This is because all the equations other than the last equation, they don't involve the right-hand side at all. And this is called the normal form. Any question? Before we proceed, I also sent out some emails last night talking about the quiz and also the logistics. Especially there's the last survey about your desire whether you want to go for PNP or go for the letter grade. So I wonder whether there are logistic questions at this point.
I was wondering if the quiz, the oral quiz, is related to the finalists the same day or is it a different day?
Oral quiz? What's oral quiz? Oral exam, you mean?
Yes, that's what I mean.
We don't know yet. Yeah, definitely it will be after, and there will be some flexibility because that won't be the last or the only final exam you need to deal with, but it should be after the final exam.
Okay, thanks.
Any other question? Okay, take that as a no, and we proceed. Now we talk about general high order equations. So let's see, y to the nth order derivative, and I have a a1 yn minus 1t. Let's assume it's a constant. You can be a little bit more general, but let's not talk about that case. Equals to some ft. You can see there's no problem at all for me to completely repeat the procedure. The second one is the derivative, and this is the n minus 1th derivative. Now I do d dt yt. So this one is y prime t, y double prime t, all the way to the nth order derivative, which is supposed to use the equation. The first n minus 1 rows, they always look exactly the same. 0, 0, 1, 0, and the last row is 0, 0, 1. So this part, so there are n minus 1 rows, and they are independent of the equation. The last row is y nth order derivative. I move everything to the right. I start from yt, so I have minus an minus 1 all the way to this term. This is minus a1. So there are n of those, start from 0 to n minus 1. There are n of those times yt. And there will be a ft on the right-hand side. 0, 0. Ft is a scalar. Again, the top n minus 1 rows is always 0, and the last one has a ft. And this is the so-called normal form. Okay, so then we can talk about the initial value problem, which is I start from dt yt, and this is a yt plus some ft, and we can start from y with some initial time t naught. This is equal to y naught, and this should be in r n. N corresponds to that. This is a nth order equation. You need to provide conditions for y0 all the way to yn minus 1, 0. And then we here assume that f is a good, ft is, let's just say, sufficiently nice. Whatever that means technically is not important for this class. So then we have that. So for this initial value problem, and it has a unique solution, then this one has a unique solution. And if we look at the equation, let's say the simpler homogeneous equation. Just ddt yt equals to ayt. So we can ask, like, first of all, should exist n linearly independent solution. We let the n linearly independent solutions be denoted by y1t, so ynt, and we can actually define the vector collecting all this all the solutions, and this matrix yt is called the fundamental solution or fundamental set of solutions. The reason why it is fundamental is because I look at the derivative. It's just taking the derivative for each one, and this is yt. It satisfies this equation. And I also ask it to satisfy y0 equals to an identity matrix. So if there's a equal to identity matrix, then why is good? Is because that is the first equation satisfy one's initial data is 1, 0, 0, 0, the other one's 0, 1, 0, 0, 0, so on and so forth. The reason why this is the case, it is fundamental, is because once I get this capital YT, now if I consider any initial value problem with a particular initial data, let's call it y0. This is in Rn. And now we can immediately have that. So this is y. The solution must be of the form yt times y0. Why is this the case? Two reasons. One, plug into the equation, and indeed this satisfies the equation. I take a derivative, this is y prime, this is a times yt times y0, and which is a times y, so indeed it satisfies the equation. Two, satisfies the initial data. It satisfies the initial data because I take y0, t0 equal to y0, which is identity. Identity times the vector is the same vector, and therefore satisfies the initial data. Therefore, it satisfies both the equation and the initial data. We have said that the solution is unique, and therefore it must look like that. Any question?
Just quick clarification, the capitalized YT is the fundamental fundamental set of solution?
Yeah. Capital YT is this. It's a matrix.
And how do we get that?
You solve it. So you solve. You solve. You just solve it for n times. This is you solve it for n times. You solve ddt small y1 vector t equals to a y1 vector t, and subject to the initial condition 1, 0, 0, 0, 0. Solve the second one with the 0, 1, 0, 0, 0, because each of this, the solution is unique. So these things are uniquely defined. Once you have solved that, and then any other equation, you can just do a H-cross vector multiplication.
Does it mean what we did before was actually a example of the fundamental solution set?
You're exactly correct.
Okay, thank you.
So, yeah, maybe I should call it fundamental solution set. I forgot which one. Let's call it fundamental solution set. Okay, so I'm gonna give you further examples to illustrate this thing. So now let's say we focus a little bit more on the homogeneous equation, and yeah, there's one, there's a two, which is the Wronski lemma still holds. We call that, so we call that the Wronski lemma basically says for second order equation, and it says that W y1t y2t, and what is the Wronski? It's y1t y prime 1t y2t y2 prime t, and it's a determinant. So now you can see that this is nothing but saying if y1 and y2, this is they form a fundamental solution set. This is exactly the determinant of this capital YT. So because this is indeed, this is y1 at t, not hat, vector t, this is y2 vector t. The Wronski lemma says that W, that's now denoted by YT, which is determinant of this matrix YT, as long as at the one point, this is not zero, this is equivalent to saying that YT is not zero for all t. You did that, I guess you did that as a homework problem for second order differential equations using the tool. Actually, the intermediate result you use is called the Abel formula. And the derivation is exactly the same thing. You can prove that the Wronski lemma for the nth order equation still holds. If at one point you have shown that this is a set of independent solutions, then at all points they are linearly independent. Any question? Okay. So now we focus a little bit more on the homogeneous equation, and let's say that we have a matrix A, and we find that it has an eigenvector. So lambda u is an eigenpair. Now I declare that yt equal to some constant ct times u, where ct is just a number, u is a vector. This must be a solution. Should be a solution for some c. Why this is true? I just plug into the equation. So ddt yt. This one is c prime t, because it's scalar, I can write it as prime times u. And I want it to be equal to a times yt, which is ctu. Ct is a scalar, I can pull it out. And this is ct. U is eigenvector, so there's a lambda, and this is u. Now I have c prime t minus ct lambda u equal to 0. Since u is not a zero vector, so the only possibility is that this scalar equation holds. And this is nothing but a first order scalar differential equation exponential lambda t. So what we have is equal to some constant exponential lambda tu should be a solution. So from this, you can almost immediately see that we can have a pretty general way to find the set of for a pretty general class of first order differential equations, we can find the solution set.
How did you jump to Ct equals to C naught e power lambda t?
Of it. This is a first order scalar differential equation. And you can
How did you get there from the previous step?
Sorry?
How did you get there from the previous step?
From here to here, or from here to here?
I can't see where you're pointing, but from the second last line.
Oh, wait a minute. You cannot see the pointer?
No.
Or is this the same thing for everyone else? Can you see the pointer here?
Okay, no, now I can see the pointer. Yes.
I see. Okay, so seems like I've been pointing all this. Okay, so it seems like the Zoom thing, I have this pen to point at different things, and seems like I have to use the mouse. Thank you very much for letting me know. And somehow, I mean, the past 10 or I don't know, 15 lectures, nobody said. Okay, are you talking about from here to here or from
Yes.
here?
From the second last one to the last one.
Second last one to the last one.
Yeah.
So this one is indeed a first order differential equation. This one is equal to 0. This is because this is a vector and it's not a zero vector. It is equal to 0. It must be that the coefficient is equal to 0.
Okay.
And this is a first order differential equation with constant coefficients.
Yep.
And before we talked about the second order differential equation, we first talked about first order differential equation, and the solution must look like that. And you can
Oh, okay. Okay.
in
Okay. The solutions are the first one. Okay.
Yeah.
Sure.
Any other question? Okay. So now you can see that for a pretty general class of systems of ODE arrays characterized by matrix A, let's assume that this matrix A is diagonalizable. If it is diagonalizable, then we can find n linearly independent. If it is diagonalizable, then we can find n linearly independent solutions called U1 to linearly independent eigenvectors called U1 to Un, corresponding to eigenvalues lambda 1 to lambda n. Some of them may be some eigenvalues may be the same, but it doesn't matter. It just says there is a some higher multiplicity. Then exponential lambda 1 tu1 exponential lambda n tun. So this one is a basis for solving the homogeneous equation for the solution set of the homogeneous equation, which is pdt yt equals to a yt. The proof is I've already shown you here. Yeah, now let me remember to use the mouse. So you just start from one eigenvector, look like this. Start from the second eigenvector, looks like that. Then at t equals to 0, this is nothing but the U1 to Un, which is already linearly independent, and therefore the Wronskian does not vanish. So the Wronskian does not vanish anywhere. So they indeed form a linearly independent set of solutions. Any question? Okay. So let me give you an example. So let's say the equation is always like this. The matrix is a 0, 1, 1, 0. First of all, let's look what this equation is. So what I'm writing here is double t equal to 0, 1, 1, 0. And this is y prime t. As you can see, the first equation really doesn't have, if it looks like the form 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, the first equation doesn't carry any information. The second one does carry information. Y double prime t equal to yt, right? So this is actually equivalent to this equation. And we have learned before we first look at the auxiliary equation, this one has two rules, and therefore the basis of the basis of the solution set is y1t equal to lambda, exponential t, y2t minus t. So this one we know. Now I would like to use the new method and solve that. And this is the old method, new method. New method is to diagonalize A. I won't repeat the procedure, and you're now pretty familiar with that. Lambda, lambda, 1, 1, and therefore the eigenvalues. So this is the, first of all, I compute A minus lambda I, and this is lambda squared minus 1 equal to 0. Therefore, lambda is plus minus 1. This shouldn't really come as a surprise, because if you want to look for exponential t, exponential minus t, its eigenvalues, according to the previous theorem, it must look like exponential t, exponential minus t. So now I solve for the eigenvectors. For 1, so this is 1, 1, 1, 1, minus 1, 1, 1, minus 1. The corresponding eigenvector, let's say, is 1, 1. And 2 is minus 1. And this is 1, minus 1. Now I know the solution takes the form. So y1t is exponential t 1, 1, and y2t is exponential minus t 1, minus 1. So if you want to extract the solution, the scalar solution y1, we only need to look at the first one. And this one gives me the y1t and the y2t. You might wonder, as the derivative, whether it is satisfied. Indeed, take the derivative here. This is exponential t, so it's indeed y1 prime t is y1t. And take a derivative here, this is minus 1, so again, a minus sign here automatically. So indeed, the two solutions, they agree with each other. Any question? Okay, so I want to say that you might think the higher order differential equations is a special case of ddt yt equals to ayt. We have shown you constructively how to do that. Not all the first order differential equations is a realization of high order differential equations. And this is, the reason is very simple. We have talked about the procedure here. Only the first order equation arrays with the A look like this and the right hand side look like this can be constructed as a high order differential equation. So now if you're given arrays, as a different A, which doesn't look like that, the previous theorem still applies, and we can still solve the problem. So let's say A is 2 minus 3, 1 minus 2. So this one doesn't really come from any high order differential equation, but it doesn't prevent us from solving that at all. So we first compute the determinant. So this is 2 minus lambda, 1, 3, 1 minus 2 minus lambda, and this is so this is lambda square minus 4 plus 3 0, and therefore this is again lambda equals to plus minus 1. Now I solve for the eigenvectors. This one is a plugging 1, 1, 3, so this must be 3, 1. And lambda 2 is minus 1. This is a minus 1, this is 3, 3, this is 1, 1. So the solution looks like C1 T 3, 1 plus C2 minus T 1, 1. And indeed, if you take this one to be the scalar part, if you want to have that interpretation, and you take a derivative, you find that it's not really a derivative. So that is why in modern scientific computing software, they are all of them, they directly target this kind of equations, first order equation arrays, because if you give me a high order differential equation, I can always solve it as a first order equation arrays. Any question? Okay, so now there's something to so there's something interesting to think about. So this is the following. I've shown you this theorem, which seems to be really general and tells you that the solution must take this form. You say, wait a minute, you definitely know high order differential equation, which is a second order differential equation. Cy 0, and I look at this auxiliary equation, and then I found that it has a repeated root. Okay, so it has a repeated root. We know that the solution should look like lambda t, y2 t equals to t times exponential lambda t. Okay, this is fact 1. Factor 2 is I can convert this thing into a first order equation array, which is t dt y equal to, this must look like 0, 1. Then I move things to the right hand side. This is minus c minus b. Okay, and if this thing is diagonalizable, if this equation is diagonalizable, and so I should get two solutions, which is called lambda 1 and lambda 1. I mean, lambda 1t, lambda 2t. It doesn't take this form. So what is the problem? So it must mean that this is not diagonalizable matrix. So when the matrix, you can work it out after the class and to really verify that this is not a diagonalizable matrix, and try to see whether you can come up with a way to handle this kind of thing. So that one goes beyond the systematic treatment of such kind of cases, goes beyond this class. If you go to Math 110, you will learn that there is a more general way of handling non-diagonalizable matrices called the Jordan decomposition, or the Jordan normal form. So the Jordan normal form is very closely related to this kind of scenarios, and we won't talk about that. Just to let you know that there's from factor 1 to factor 2, there's no contradiction. So another thing I want to say is I talked about the fundamental solution set. It turns out, for written this for really a lot of times in this class, and start from y0, y0. So this one, actually the solution has a closed form. I say, wait a minute, this doesn't look quite right. So we have everything in the past 2 weeks, what we have been doing to solve a special case of this equation. And we really tried very, very hard. We go, check the auxiliary equation, high order things, maybe I need to worry about more things. And those are only high order differential equations. And those are only some special cases of where was it? Those are only some special cases of this first order equation arrays, and we can barely manage to handle the case where A is diagonalizable. And now you tell me that there's a closed form solution for all A. Actually, everything did adds up. The solution just looks like this. Okay, so I put this exponential AT, this is called matrix exponentiation or matrix exponential function. So first of all, of course, how to define this matrix exponential function at all. So this, I don't think we have enough time to talk about this topic in this class, because we also have the partial differential equation to worry about, but it is a pretty cool fact. So the fact that everything we have learned so far is covered by this very, very concise and formula, just the exponential AT. And if you're interested, read 9.8. So 9.8 is not covered in the final exam, but only if you're interested in knowing why it could be possible at all to have such a simple formula. And this is not required. Okay, any other question? Let me finally talk about a thing that is indeed covered in this class, which is how to deal with inhomogeneous equation. First order equation. So dt yt equals to a yt plus f hat t. Again, this covers all the previous inhomogeneous high-order differential equations. And the technique I want to introduce is called variation of parameters. Variation of parameters, it again includes all the, so let's see, we're interested in the case where ft takes this form. So now, so takes this form, where this is exponential rt times t to the mth power, t to the lth power, times a fixed vector called g. In particular, all the previous cases can be covered by considering g to be 0, 0, 0, 1. Okay, everyone's okay with that statement? All the inhomogeneous high-order differential equations can be covered by the case here. This is because only the last one contribute to the right-hand side, which is exactly this. And we have talked about it before. For this kind of thing, the particular solution must take the following form, exponential t, and then inside I can do some sort of like a mth power tm a0, where m may be L, usually m is L, but it can be L plus 1, L plus 2, depends on whether you have repeated roots or so on and so forth. Depends on the relation between R and the roots of the auxiliary equation. Just like here, there's a very concise formula. I'm going to give you a very concise formula that would cover all the cases, including this case, but also beyond. This is called a variable parameter. What is the variable parameter? So let's start with the fundamental solution set, which is I have defined dyt dt equals to a yt, y0 is identity. Now we assume that this matrix is given. Given means that I've solved this problem with this particular initial condition. I know that if I want to represent the solution of a homogeneous equation, so initial condition small y0 is some given vector, I just need to have yt times that vector. But now, in order to find a particular solution for the inhomogeneous equation, I make a very educated guess times a vector ct. So recall that this one should be a constant vector if we're dealing with a homogeneous equation. And this ct is, and ct is nothing but the initial is equal to c and given by the initial data, as we talked about at the beginning of the class. Now we deal with the inhomogeneous equation. This vector ct can be time dependent. Okay, that's what we allow. It's not that clear at this point that this is sufficient, because especially recall this kind of thing. It looks pretty complicated. I mean, it's not that clear at all that this will indeed give me a particular solution, but the statement is it will. Why? I take the derivative, dt ypt. So there are two of them. They both depend on t. So Leibniz rule, yt, this is a c dot t. Okay, so or ct dt. So this one satisfies the equation. So this is A, YT/CT, so this is small y PT. We use the equation. And this one is YT/C dot T. And what we want is this is equal to AYPT plus FT. So this cancels. If we can solve Y inverse T FT, then we're done. But you see, the right-hand side doesn't even involve C. So this one is just a C1t equals to some known function called D1, C2t dot equal to some known function D2, so on and so forth. So I can just integrate and find that CT actually has a closed form solution, is a constant vector C times 0 integrate out, and this is YT FT, you have a dummy S ds. And therefore, YPT is equal to YT, the fundamental solution set, times the vector C plus YT 0 to T Y inverse S Fs ds. So it looks complicated, but I would like to say that all of these things are computable. Yt, the matrix, this is a function has been given. How to compute this inverse is not that easy, but this thing definitely exists. This guy and is a known function. You integrate out, multiply with that y, and you will get that. And in the book, so there are more detailed examples showing you that for what's a more consistent way of understanding the formulation here and the formulation here. Indeed, as you can possibly understand, that since this is a completely general formulation, this method of coefficients must be a special case of variation of parameters. It is indeed true. However, again, as is true for many general formulation, if you want to compute the answer for a specific problem, this one may turn out to be more complicated, just like this one. The matrix exponential function is well defined, it's very beautiful, but in terms of actual computation, the previously discussed theorem is much easier to use. Similarly, for the inhomogeneous equation, the method of undetermined coefficients is a lot easier to use. Okay, so this is all I want to talk about for the ordinary differential equations, which means that the function of interest only depends on one variable. We can call it t, you can call it x, call it some other things, but there's only one variable. Starting from Friday, we're going to talk about the last chapter of this semester, which is partial differential equations. Any questions?